Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at working with a prime modulus. We're looking at arithmetic modulo p where p is a prime. So this is used extensively in things like computing and cryptography because when the modulus is prime, arithmetic works the same way as it does with real numbers, the numbers that you're used to. So, for example, when you're working with a prime modulus, all non-zero elements are units. That means you can divide by any number that is not equal to 0, exactly what you can do with real numbers. Because all the non-zero elements are units, it means you can solve all the linear congruences. You don't get all those situations where there's multiple or zero solutions. In a prime modulus, it's also really easy to calculate phi of p, and you don't have zero divisors other than 0. And that's the way it works in real numbers. In real numbers, you don't have those situations where 4 times 5 is equal to 0, which it is in, say, modulo 20. So working in prime modulus just makes things nice and easy. So we're going to look specifically at primitive roots and quadratic residues, which themselves are used a lot in cryptography. So a primitive root is a number A that satisfies this and this. So what is this saying? Well, we know that modulo p, where p is a prime, this is true for any value of a to the power of p minus 1 is always going to be equivalent to 1 mod p. What makes it a primitive root is if this is the smallest number to which you can raise a to get an answer of 1. That's what this is saying here. A to the power of n is not equivalent to 1 mod p when n is less than p minus 1. So primitive roots cycle through all the units modulo p with their powers. Okay, probably doesn't make a lot of sense. Let's look at an example. So we're going to look at each of these powers of 3 and powers of 4. We're going to do this in mod 5. So in mod 5, 3 to the power of 1 is obviously equivalent to 3 mod 5. 3 squared is 9, so that's 4 mod 5. 3 cubed is 27, which is 2 mod 5, and 3 to the power of 4 is equivalent to 1 mod 5. So note that in mod 5, because 5 is prime, 1, 2, 3, and 4 are the units in mod 5. So you can see that each of the powers of 3 is a different unit in modulo 5. You can see 3 to the power of p minus 1, p is 5 here. 3 to the power of 4 is 1, but 3 to any lower power is not equivalent to 1. So it turns out 3 is a primitive root modulo 5. What about 4? Let's go through the powers of 4 modulo 5. 4 to the power of 1 is obviously 4. 4 squared is 16, which is 1 mod 5. Turns out that 4 to the power of 3, it's just going to be 1 times 4. 4 to the power of 4 is 1. Turns out if you take powers of 4 modulo 5, they're always going to be 4 or 1. The powers of 4 are just going to cycle 4, 1, 4, 1. There's no power of 4 equal to 2 or 3. So it turns out 4 is not a primitive root modulo p. Certainly 4 to the p minus 1 is equivalent to 1, but that's not the lowest such power for which that's true. There's a number less than p minus 1, i.e. 2, for which 4 to that power is equivalent to 1. So this is what it means to be a primitive root. It means the first power of the number to be equivalent to 1 is p minus 1. It means that the powers cycle through each of the units. Each power is a different unit modulo p. So there's no really easy way to find primitive roots. It turns out there are always primitive roots modulo n. That works even when n is not prime. We're just restricting our attention to prime modulus because it's really easy to work in prime moduli. So you won't be asked to just come up with a primitive root because, as I said, there's no easy way to do that. So let's go ahead and look at quadratic residues. So a number a is a quadratic residue if there exists an x such that x squared is equivalent to a modulo p. Basically what this means is a is a perfect square modulo p, and it means that you can square root it. So let's look at some examples. It turns out 3 is a quadratic residue modulo 11 because 6 squared is equivalent to 36, which is 3 mod 11. 36, when divided by 11, leaves a remainder of 3. So 3 is a quadratic residue because it's equivalent to 6 squared. 3 is a perfect square modulo 11. On the other hand, 6 is a quadratic non-residue. That just means it's not a quadratic residue. There is no number that you can square in order to get 6 mod 11. So you can square root 3 modulo 11. Square root of 3 is 6 in mod 11, but you can't square root 6. Remember that in modular arithmetic, we don't have decimals. So you can't write this as, 2.45, blah, blah, blah. Okay, let's look at how we actually find which numbers are quadratic residues modulo p. So it turns out that the quadratic residues can be found by taking the even powers of any primitive root. Doesn't matter which primitive root it is. So 2 is a primitive root modulo 11. So if I tell you that, you can find all the numbers that are perfect squares modulo 11 by taking even powers of 2. So 2 squared is equivalent to 4 mod 11. No surprise there. So to get 2 to the power of 4, it's just 2 squared squared again. So 2 to the power of 4 is 4 squared, which is 16, and 16 is equivalent to 5 in mod 11. So how would you get 2 to the power of 6? Well, 2 to the power of 6 is equal to 2 squared cubed. So 4 cubed is 64, and 64 is equivalent to 9 mod 11. So how would you get 2 to the power of 8? Well, you can just take 2 to the power of 4 and square it. 2 to the power of 4 was equivalent to 5 mod 11. Square 5, you get 25. 25 is equivalent to 3 mod 11. So last one is 2 to the power of 10. There's a few ways you can get it. You might just get it by doing 2 to the power of 8 times 2 squared. However you want to get it is fine. 2 to the power of 8 was equivalent to 3 mod 11. 2 to the power of 2 was equivalent to 4 mod 11. And so 3 times 4, which is 12, is equivalent to 1 mod 11. Remember that when working modulo p, any non-zero number to the power of p minus 1 is always equivalent to 1 mod 11. 1 is always a quadratic residue. So the quadratic residues mod 11, we have 1, 3, 4, 5, and 9. So these powers of 2, there are always p minus 1 on 2 of them. So when you're doing modulo 11, 11 minus 1 on 2 is 5. There are 5 non-zero quadratic residues, so we can stop there. We don't need any more powers of 2. So just note that 0, you have to add on that. That is always a quadratic residue regardless of the modulus. Some textbooks, if they list quadratic residues, will only list the non-zero ones. I don't care whether or not you include 0, but just be aware 0 is technically always a quadratic residue, as is 1. So these are all the numbers that you can square root modulo 11. All the other numbers modulo 11, like 2, 6, whatever, they are quadratic non-residues. They don't have a square root modulo 11. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.